Hello everyone, welcome back to our channel. Come to the next reaction, Appel reaction. Before going to discuss about this particular reaction, let's see some fundamental points. We all are very familiar to their nucleophilic substitution reactions, right? The general formula is what? If Rx is treated with O minus, what will happen? The X is removed in the form of X minus and you will come up with what? OH. Simply, in this transformation we have seen conversion of alkyl halides into corresponding alcohols. X minus is replaced with OH minus. Right? Here we are having two types of substitution. SN1 substitution and SN2 substitution. Nucleophilic unimolecular substitution and nucleophilic bimolecular substitution. If you see these two kind of reactions, what we are observing in case of the SN1 reaction, whatever the nucleophile we are having, the nucleophile may approach the reactive center either from the front position or either from the back position. That's why what happens in case of SN1 reaction, we are getting mixture of products, right, with same configuration, with retention of configuration and with inversion of configuration. But in case of the bimolecular reaction, what we are observing, the nucleophile is going to be always attached to that particular reactive site from the opposite position. If the X is in the front side, the nucleophile is going to be attacking from the back side. If the X is in the back side, the nucleophile is going to attach it from the front side. This is the what fundamental concept we all know in case of SN1 and SN2 reaction. The Appel reaction is similar to what we call it as SN2 type of reaction. If you see the statement, conversion of alcohols into alkyl halides with PH3P, triphenylphosphine and CX4, tetrahalomethane, is commonly called as Appel reaction. Already we know that conversion of alkyl halides into corresponding alcohols. Here what we are observing, the reverse phenomena or not, conversion of alcohols into alkyl halides, but the reagents are what? Triphenylphosphine and CX4, tetrahalo. Next, general equation of this particular reaction. The reactant is alcohol. Assume that the OH group in the front side. We are treating this one with what? CX4 in presence of triphenylphosphine. It can produce as alkyl halide. The OH is replaced with X. But here the thing is that what? Here OH is in the front position, in the product, the X group in the what? Back side. This is a kind of SN2 substitution or not? But the reverse of this particular reaction. Let us see the mechanism. How the alcohols are converted into corresponding alkyl halides with inversion of configuration. Mechanism. Initially we have taken triphenyl phosphine. It is going to treated with what? CX4. CX4. Already we know that the phosphorus is having what? Lone pair of electrons. It can donate its lone pair of electrons to the positive center. In this case, what happens? One of the CX bond in which the single bond move towards carbon atom. Thereby what happens? Carbon will take minus charge, the X will take positive charge or not. Here we have created a positive charge, thereby what happens? These lone pair electrons donated to this positive charge. Thereby we will come up with PH3P connected to X donated lone pair electrons. That's why it attains positive charge. The carbon is having CX3 and this one will become what? Minus. CX3 minus. This one is called as Appel salt. The combination of triphenyl phosphine corresponding halide and CX3 minus. This is the intermediate which is produced during the formation of your final product. Right? This is very important step. What is the intermediate in this particular reaction? That is the what? Appel salt. This is the representation of Appel salt. So what is the reactant? It is an alcohol or not? Now the alcohol is going to treated with this particular Appel salt. The representation of alcohol is what? R OH. The hydroxyl group present in the front side or not? This is the representation. Let us see how this particular moiety is going to combine with this particular Appel salt. Right? For that purpose I am writing arrow in this way. Initially what happens? Here we have CX3 minus or not? It needs a positive charge. That's why what happens? Whatever the OH group we are having here this single bonding electrons move towards oxygen atom. Thereby what happens? Oxygen will take negative charge. The hydrogen is having positive charge. CX3 minus and H plus. Removed in the form of what? CHX3. CHX3 will be removed. That is a halo form or not? Halo form removed. Then we will come up with what? R O minus. The reaction takes place at the oxygen but not at the carbon. That's why the front direction remains same. Okay. Now we have O minus and here we are having what? PH3 P plus X. This moiety is going to treat it with your phosphorus related moiety. Let us see. The O minus is going to attack the phosphorus. It means that what? The single bond is going to be formed between the oxygen and phosphorus. At the phosphorus, the valence is increasing or not? That's why what happens? The X is removed in the form of X minus. So, we will come up with R, oxygen still in the front side. This is oxygen. Oxygen is connected to phosphorus. After the phosphorus we are having 3 phenyl rings. The phosphorus having its positive charge. Here what happens? X is removed in the form of X minus. In the next step, what happens? The X is removed, the X minus is going to attach at this carbon center. If the X minus is going to attach at this carbon center, here we have a bulkier group or not? OPPH3 plus. The bulkier group will not allow the X minus. Why? Because X minus is very smaller in nature. That's why there is no possibility for the X minus to approach that particular carbon from the front side. So always the X minus is going to attack at this carbon through the back side or opposite side. Thereby what happens? This bond will move towards the oxygen. So oxygen will take the minus charge. This minus and this plus will create a pi bond. That's why it can be removed in the form of phosphine oxide. Phosphine oxide will be removed. Then the the X is approaching from the what? Back side or opposite side. You will come up with your product. This is what we call the mechanism of Appel reaction. Very simple or not? Let's see the applications. Let's see the applications. This is the first application. If you see this reactant, it is a carbohydrate or not? At this particular carbon, this carbon is commonly called as what? Anomeric carbon. At the anomeric carbon, we can have the substitution. Here we are creating what? A nucleophile or not? That is Br minus. The Br minus is going to replace with what? OH. If you observe this particular OH group, here it is in the equatorial position or not? That's why whenever this reaction is subjected to Appel reaction, what will happen? The Br minus will be attacking from the axial position. Simply here we can attach Br. The product will be this is OBN. I can write in a clean way for your understanding. OAC, OBN, OBN, OBN. This is Br. The first example of Appel reaction. Let's see the second example. We have 5-membered ring. In the 5-membered ring, we are having CH2OH group. Simply, if this one will treated with, this is Br4, PPH3, heating. Simply what happens? The OH will be replaced with what? Br. The last application of this particular reaction is the reaction is saying that we can convert OH into the corresponding halide. The last application is very important application. Here we are going to observe that the effect on carboxylic acid. Till now we have discussed about the what? Alcohols, right? The similar kind of effect is going to be observed in case of carboxylic acids also. From these carboxylic acids we can synthesize or we can prepare oxazoline derivatives. We all know that oxazoline compounds are very important heterocyclic compounds. They are used as intermediates in the preparation of different kinds of the pharmacologically active drug molecules. That's why we are going to have a particular application for this Appel reaction. See that RC double bond OH initially going to treated with CCl4 and PPH. We all know that in the mechanism these two can combine together to form a Appel salt or not. That Appel salt is what? PH3P positive charge Cl and CCl3 minus. In the first step what happens? From this OH the H plus will be removed. This H plus and CCl3 removed in the form of CHCl3. Then we are having O minus. The O minus is going to approach us what? This phosphorus. It can be removed Cl minus or not. So we can write RC double bond O oxygen. This is connected to phosphorus and we are having 3 phenyl groups with positive charge. If this kind of species is going to treated with the compound called as amino alcohols, NH2OH, amino alcohol. What happens? Nitrogen containing lone pair of electrons. These lone pair of electrons will be donated to this carbon. Thereby what happens? The oxygen will take minus charge. Right? Let us see. Here we are having two reactive centers. One is NH2 and another one is OH. Here I have donated nitrogen lone pairs but not the oxygen lone pairs. Why? Because the concept of chemoselectivity. According to chemoselectivity, what happens if you have more than one reactive center? The reagent is going to use only one particular reactive center by leaving behind the other potential reactive centers. The reason for the donation of this particular nitrogen lone pairs is that the nitrogen electronegativity is lesser than comparing with the oxygen. That's why nitrogen can easily donate its lone pair of electrons to the electron deficient center comparing with the oxygen. Thereby we are observing what? RC double bond O. This is connected to nitrogen. Nitrogen is connected to CH2. Again CH2 and this one will become what? OH. Nitrogen donated its lone pair of electrons. That's why nitrogen is going to have positive charge. This is one case. After that what happens? In order to maintain its valency, the nitrogen loses its proton. So it can produces RC double bond O single bond N H CH2, CH2 single bond OH. Okay, this is the molecule produced from this particular species. Now let us see, this is going to have the treatment with this particular moiety. pH3, P plus and Cl minus. Simply what happens, for the convenience purpose we can write this one in this way. Again oxygen donated its lone pair of electrons to this one. The Cl will be removed in the form of Cl minus. Thereby what happens, here we will observe OH plus. In order to attain its valency, what happens, here oxygen will be removed in the form of, oxygen can attains its valency by the elimination of hydrogen in the form of H plus. So you will come up with, for my convenience I am writing the compound in this way, RC double bond O, single bond NH, this is CH2, CH2, now this one will become oxygen, oxygen is connected to phosphorus, CH3, positive charge. Again, the nitrogen lone pairs involving in the conjugation with the carbonyl oxygen. Here see this, the oxygen atom is going to get what? Negative charge. This negative charge is going to attach at this carbon. Thereby what happens? The single bonding electrons move towards the oxygen. So you will come up with pH3, P plus and O minus. This one will become what? Triphenyl phosphine oxide. This one will be removed and you are going to have R oxygen. See this one, R is connected to carbon, R is connected to carbon, carbon is connected to oxygen, oxygen is connected to another carbon, another carbon, this carbon is connected to another carbon, this carbon is connected to nitrogen, nitrogen is connected to this carbon. Here what happens, the pi bond between nitrogen and hydrogen takes place. Nitrogen is having positive charge. In order to maintain its valency, what happens, the hydrogen will be removed in the form of what? H plus ion or not. So it can produce N oxygen pi bond, this one is R. These kind of compounds are commonly called as what? Oxazolines. So we have started the application with what? Carboxylic acid and ended with what? Oxazoline moiety. It's very important moiety. So this is one of the beautiful application of Appel reaction. So this is all about Appel reaction.